pencil writing is quiet, yes. Okay, so today we're going to talk about graphing linear functions. We have done this before. We called them linear equations, but an equation is the same thing as a function. So it says to graph a function, use the coordinate plane. Place input values along the horizontal x-axis and output values along the vertical or y-axis. Okay, and then this part right here where it talks about discrete and continuous, I'm going to come back and talk about that, okay, in just a second. So let's look at example number 1. Okay, it says a rock climber is 200 feet above the base of a cliff. Let me try to make this a little bit closer. There we go. Okay, above the base of a cliff. The climber is climbing at a rate of 10 feet per minute. Make a table to describe the climber's height above the base of the cliff, which would be the output, as a function of time that has passed, which is the input. Okay, and so it tells us over here that input is going to go along the x-axis. Okay, and then up here it tells us that the time that has passed is the input. Okay, so I'm going to label this as time passed. And then it says their height above the base of the cliff is the output. So, height above base. Okay, so let's go ahead and make some input-output pairs. Okay, so where's the rock climber starting? Okay, read that first sentence again. It says the rock climber is 200 feet above the base of a cliff. Okay, so at minute 0, he or she is already 200 feet above the base. Okay, then it says they're climbing at a rate of 10 feet per minute. So after a minute has passed, they would be at 210 feet. Then 220, 230, 240, and 250. Okay, so now we have all these input-output pairs, right? At minute 0, he was at 200 feet. At minute 1, 210. At 2, 220. Okay, and so on and so on. So we have to figure out how to put this in a graph. So I know that I'm going to put 0 here, 1, 2, 3, 4, 5 minutes. Sorry, this is kind of crammed in there. Okay, that's a 5. And so I know that I need to go from 200 up to 250. So I'm going to go ahead and I'm going to put a little break. Okay, it's like a little zigzag to show that there's data in between here and here. And I'm going to start it at 200, 210, 220, 230, 240, and then 250 feet. So now I'm just going to graph my input-output pairs. So at minute 0, okay, the climber was at 200 feet. After 1 minute, he was at 210, 220, 230, 240, 250. I'm going to connect them with a line, okay, and then it's going to have an arrow on it to show that he could keep climbing. Okay, and this is a solid line. This is kind of what I was going to talk about. This is what's called continuous data. That's where there are numbers between any two data values that have meaning. Okay, so for example, if I said, well, where was he after a minute and a half, right? We could come over here and say, well, after 1.5 minutes, he was probably at about 215, right? This data in between 1 and 2 minutes right here, it has value. Right? He's not jumping from 210 to 220, he's gradually climbing up. Or if I said, where would he be after 4.5 minutes? So this is 4, this is 5, so 4.5. And then I could take it over to here and say, oh, he's probably at 245 feet. This little point has meaning. And so we're going to use a solid line to indicate that this data is what we call continuous. Okay, and in a minute, I'll show you what an example of discrete would be. Okay, let's look down here at this bamboo example. Okay, it says a bamboo plant is 23 centimeters high, and it grows 16 centimeters a day. The plant's height, the output, okay, so spoiler alert, gosh, I keep hitting my little stand. So I'm gonna put height here, because I know that output goes along my y-axis. Okay, depends on the number of days that have passed, which is the input. Oops, so days passed. So, okay, graph the function. So let's just say, okay, well, if my days, and then I have my height, right? And I'm trying to figure out what they're gonna be. So at day 0, then I'll just do 1, 2, 3, 4, 5. So at day 0, how tall is my plant? What am I starting at? Right, my plant is starting off at 23 centimeters. And it's growing at a rate of 16 centimeters a day. So after 1 day, that would be 39. And then we add 16. Day 2, it's at 55. We add 16, 71, 87, and 103, right? All I did every time was add 16 because it's growing 16 centimeters a day. So 23 plus 16, 39, plus 16, 55, right? 71, 87, and 103. Okay, so what I'm gonna do is I am gonna say down here, this is 0 days past, 1, 2, 3, 4, and 5 days past. Okay, and then going up the side, I'm gonna need to go from 20 to 103, so I'm just gonna count by 20. 20, 40, 60, 80, 100, 120. So now I'm gonna take the data and I'm gonna plot it. And I don't have to be, I mean, I wanna be pretty close, as close as I can be, but I don't have to be perfect. So on day 0, it was just above 20 at 23. Okay, on day 1, it was at 39, which is at almost 40. Day 2, it's at 55. So 20, 40, 60, so maybe like right there. Day 3, it's at 71. 20, 40, 60, 70 is gonna be right there in the middle. Day 4, it's at 87. 20, 40, 60, 80, so almost at 90. And then day 5, it's just over 100. Okay, and then I have to decide, is this continuous data or discrete? Okay, and it's gonna be continuous because the plant doesn't jump from 23 to 39, right? It's growing constantly. So again, we could say, well, what about at 2.5 days? Okay, so day 1, day 2, so day 2.5, it would be at probably about 63, which would be right about there. Okay, so questions on that one? Okay, so the next one, it says, determine whether the data for each function are discrete or continuous, then make a table and graph the function. So pretty much exactly what we've been doing. So a gallon of milk costs $2.59. The total cost of G gallons of milk is a function of the price of each gallon of milk. Okay, so if we have the number of gallons and the cost, do the gallons depend on the cost or does the cost depend on the gallons? The cost is going to depend on the gallons. So gallons are going to go down here and our cost is going to go up the side. Okay, and I know that I'm doing 1 gallon, 2 gallons, 3 gallons, and 4 gallons of milk. So it tells you at the top that a gallon of milk is $2.59. So 1 gallon is $2.59. So $2.59 plus, say, add another $2.59, that's $5.18. What if I bought 3 gallons of milk? 3 times $2.59 is $7.77. What if I bought 4 gallons of milk? 4 times $2.59 would be $10.36. Okay, so I'm gonna graph my data. I'm gonna have to go from $2.50 up to 10. So I'm gonna count by 2. I'm gonna make it, let's see. I'm gonna make it easy on myself and I'm just gonna go by 2s. 2, 4, 6, 8, $10. Okay, so now I'm gonna take my data and 1 gallon of milk was $2.59. So right about there. Okay, 2 gallons of milk was $5.18. 3 gallons was $7.77, so pretty much 8. And 4 gallons was just over $10. Okay, this is our first example of discrete data where we're gonna use a dashed line to connect our dots because can I buy in between, like if I said, okay, well what if I had a dot right here? Does that represent anything? When you go to the store, okay, and we're talking about like gallon jugs of milk, can you buy 2.5 of those? No. right? If each one is $2.59, you can't say, well, I just want a little over 2 gallons. You have to buy it by the gallons. So this makes it discrete. Okay, discrete data are data that involve a count of items, such as the numbers of people or numbers of cars. For discrete data, indicate each data item with a point and connect them with a dashed line, which is what we did. Okay, so look down here. It says during, that should say, during 1 hour of walking, you burn 257 calories. The total number of calories you burn is a function of the hours that you walk. Okay, so the calories are depending on our hours walking. So calories are going to go up the side. Hours walking is going to go down here. Okay, so if I walk for 1 hour, it tells me I'm going to burn 257 calories. So what if I walk for 2 hours? 2 times 257 means that I'm going to burn 514 calories. Well, what if I walk for 3 hours? That's 771. Okay, so I'm going to go 1, 2, 3, 4, 5, 6, 7, 8. I'm just going to add an 8th one up there. And now I'm going to plot my data. So if I walk for 1 hour, I burn 257. So in between 200 and 300. 2 hours, I burn just over 500. So 1, 2, 3, 4, 5. And 3, I burned just under 800. And then is this going to be a solid line or a dashed line? What do we think? Are you burning, can you only burn like 257 and then 514? Or can there be data in between here that has meaning? Okay, the data in between has meaning, right? You can walk for 1.5 hours and you would burn, what would that be? Like close to 400? Okay, so this data in between has meaning, so we use a solid line. Okay, I think this is my last example like this. It says the function h equals 4,000 minus 600m represents the height of a skydiver in feet after the diver has been falling for m minutes. Okay, so he's starting at 4,000 feet, and every minute he's dropping 600 feet. Okay, so what's going to be our input, right? We have height and we have minutes. So what depends on what? Does the height depend on the minutes or the minutes depend on the height? Okay, his height is going to depend on how many minutes he's been falling. Okay, so let's just say 0 minutes, 1 minute, 2 minutes, and 3 minutes. Okay, so he's starting at 4,000 feet. Okay, so at minute 0, he is at 4,000 feet. Then he's going to, hey guys, then he's going to drop 600 feet after the first minute. So he's at 3,400. Then he drops another 600. So now he's at 2,800. Then he drops another 600, 2,200 feet. Okay, so I'm going to go ahead and start mine. Let's see. I'm going to do 1,000, 2,000, 3,000, 4,000. Whoops, I should have put height and minutes. Okay, so at minute 0, he is starting at 4,000 feet, right? After 1 minute, we said he was at 3,400. After 2 minutes, he was at 2,800. After 3 minutes, he was at 2,200. And it's going to be a solid line. And notice it's going down because his height is actually decreasing, right? The longer time goes on, the lower he gets. Okay, let's look at the second page. Okay, and this should be very, very familiar. It says a linear function is a function whose points lie on a line. You can write a linear function in the form f of x equals mx plus b, right, which is the same as y equals mx plus b. Then you can use the y-intercept and the slope to graph the function. M is our slope, that's rise over run. B is the y-intercept, which is where it's crossing the y-axis. I'm trying to raise this up so I stop hitting it with my hand. Okay, so let's look at this one. The function is y equals 2x, I'm going to write it down here, minus 3. Okay, so the slope is always the number that comes in front of x, so that's 2. Okay, and I want my slope to be a fraction. Mason. So I want my slope to be a fraction, so I make it 2 over 1. And then the y-intercept is this number right here, so that's -3. So I'm going to start my line at -3, and then my slope is rise 2, run 1, rise 2, run 1, rise 2, run 1. I'm going to connect them with a straight line, and that's it. Okay, let's look at this one. Okay, y equals x minus 1. Okay, so you might be like, well, there's nothing in front of x. Well, if we just have x, that's like saying 1x. So that's 1, and if I have a whole number, I put it over 1. And then my y-intercept is this number at the end, -1. So I start on the y-axis on -1, and then I rise 1, run 1, rise 1, run 1, rise, run, as many as I can. I'm going to connect them with a solid line, and then I'm done. Okay, number 9. Same thing, y equals -1/4 x plus 3. So the slope is this number in front of x, which is -1/4, and my y-intercept is 3. So I'm going to start on 3, 1, 2, 3, but this time it's negative slope. So instead of going up and to the right, I'm going to go down and to the right. So down 1 over 1, 2, 3, 4. I'm going to connect those with a solid line, and that's my graph. Okay, so why don't you pause it and then come back and I'll show you how to do these last two we can check. Okay, on number 10, the slope is going to be 5 because it's 5x, and if it's a whole number, I'm going to put it over 1, and then the y-intercept is 0 because we're not adding anything at the end. So I'm going to start it at 0, and I'm going to rise 1, 2, 3, 4, 5, run 1. I'm going to connect my dots, and that's what my graph should look like. Okay, over here you should have -1 over 1 as your slope, and the y-intercept is +6. So I'm starting at 1, 2, 3, 4, 5, whoop, 1, 2, 3, 4, 5, 6, and then my slope is down 1 over 1, down over. Remember when we talked about slope, dude, right? Negative slope means nice negative. Okay, it's the same idea.